All right, we're gonna give this a shot. So this is graphing practice, determining slopes and equations. The student decides to analyze the motion of a BB in a tube full of alcohol as it moves down an incline of medium steepness. In order to increase the time increments, the metronome is set to click every second while the student records the position on a piece of paper. The picture shown above shows where the objects were and the data table has already been provided. Note that the initial position of the BB at a clock reading of 0 was 0. First of all, they ask, what is the independent variable for the experiment? Well, if you're not quite sure, you should go look at your notes and find out what an independent variable is. Pause the video at this time, go look at your notes and figure out which would be the independent variable. Once you've looked at your notes, you know that the independent variable is what you're going to preset. And in order to have equal amounts of changes in time, they preset increments of time with the metronome. On the flip side, okay, so our independent variable is clock readings or time. And again, that's because that's what they preset before the experiment. It's a variable important enough to change or preset before the experiment. What is the dependent variable for this experiment? Well, that's the one that is dependent on the outcome of the experiment. So they said they were going to record the position on the piece of paper with a marker. And our data table should have our dependent variable in the second column and our independent variable in the first. So our dependent variable, again, is position. And the explanation is that's what we're recording as a result of the experiment. Next up, you're supposed to make a proper graph. You might want to go back and look at your other graphs and see what the expectations were for that. To do that, we've got a sheet of graph paper. We're gonna give our left-hand margin a little bit of space so we can write names of variables and stuff. We're gonna set the ruler up on one of the natural grid lines and draw the y-axis. Next, we're gonna give ourselves a little more than a ruler's width down here at the bottom, set it up on the natural grid lines, and draw the x-axis. So we know that for this axis, we're making this position because it's the dependent variable. We can use the symbol with an X with a vector. And according to our sheet, it looks like we're going to be measuring in centimeters. We've got clock readings on the x-axis, which is where the independent variable goes. And that's measured in clicks, which is similar to beats of the metronome that we did before. And next up, we need to show an appropriate way to calculate the scale for each of the axes. If you don't remember how to calculate an appropriate scale for each axis, pause the video at this time, go back and look at your notes. How do you make an appropriate scale for clock reading if our biggest clock reading was 9 clicks, and you'll need to count the number of boxes across here. Pause the video, go look at your notes and try to figure that out. Please push play when you're ready. So now that you've looked at your notes, we know that to scale the x-axis, you need to take the max clock reading and divide by the number of boxes along the x-axis. Boxes along the x-axis. Our biggest clock reading is 9 clicks, and our biggest number of boxes I counted across, and it looks like there's 25 boxes down here. We feed that into a calculator, and you got 9 divided by 25 equals 0.36 clicks per box, but we're not allowed to go up by 0.36. We have to go up by multiples of 1, 2s, 5s, and 10s. So in this case, what's bigger than 0.36? It's 0.5 centimeters per box. Likewise, if you need to know how to scale the position axis, please use this format, but for the biggest position divided by the number of boxes along the y-axis, and calculate that. Please pause the video, do that, come back and check this for accuracy. So our biggest position, our max position, divided by the number of boxes along the y-axis. our biggest position, it looks like, is 107.5 centimeters divided by, oh my goodness, I realized just now that for my clock readings, I put 5 centimeters on the top instead of 0.5 clicks on the top. Down here, biggest position, 107.5 centimeters divided by the number of boxes. Counting the boxes all the way up here, I came up with 34 boxes. 34 boxes along the y-axis. And so we go ahead and punch that in. 107.5 centimeters divided by 34 boxes equals 3.16 centimeters per box, but we're not allowed to go up by 3.16, but we are allowed to go by 1s, 2s, 5s, and 10s. What number is bigger than 3.16? And that'd be 5. 5 centimeters per box. So the x-axis, our clock readings are going up by half a clicks. Our vertical axis, our position, going up by 5 centimeters. So coming down to the clock reading axis down here, this is 0 clicks, a half click, 1, 1.5, 2, 2.5, 3, 3.5, 4, 5, 6, 7, 8, 9 clicks. Going up the y-axis, we said we'd go up by 5 centimeters per box. So that's 5, that's 10, 15, 20. I'm gonna go ahead and skip to 30, 40, 50, 60, 70, 80, 90, 100. It'd be 110, 120. Oh, I've gone up big enough. Our biggest one is 107.5. Next up, pardon me, we need to make sure that we plot the points and use point protectors. So I'll have to look at the data table. At 0 clicks, we've got 0 centimeters. So we're gonna plot our point and put a point protector. At 1 click, you're at 12.5, 1.5. 12.5 would be exactly halfway between 10 and 15, and a point protector. 2 and 24.5. Here's 2, 25 would be here, so 24.5 is gonna be just below that. 3, 37.5, which would be exactly halfway between 35 and 40. So there's your point protector. Next up, you've got 4 and 49. 4 and 49, that's gonna be just before the 50. 5 and 60. That's a nice clean number. Next up, we've got 6 and 72.5. 6 and 72.5 is actually gonna fall exactly between 75 and 70. So it's gonna go right there. 7, 84.5, 7, 80. This is 85, so 84.5 is just gonna be a hair underneath there. Plot your point with your point protector. And lastly, 9 is gonna be at 107.5, which would be, let's see, here's 100. Did I miss one? Oh, I did. 8 is at 96.2. Here's 90, here's 95. 96 would be here, so 96.2 here. And then 9 is 107.5. Here's 105, here's 110, so 107.5 is exactly between the two. And now we'll need to pull out a ruler to do a line of best fit. I kind of like to look at the ruler on the side like this to see, make sure all the points are somewhat lined up along there. Maybe bring it in from the side. Sometimes you're lucky enough for the slope or the best fit line to go right through 0, 0. It looks like we might be lucky enough for that to happen today. Try to line all these up to the best of our ability. Make sure that we can drive it all the way off this side of the graph and go through the y-axis. Lining this up multiple times to make sure that we've got something that's pretty decent. Looks like most of those are hitting right along there, and we'll just do one single line. Does that look like it hit most of them? It looks like it hit most of them. Now we need to find slope points. Find spots where the best fit line naturally intersects with the grid lines. Here is a great one right here. And the coordinates for that, it looks like, are 10, clicks and 120 centimeters. And then coming along here, we've got, this is close to the corner, that looks right on the corner, 60's right there. This looks like another good one. Do we have any closer down here? That's close to the edge, but not perfect. I think our next best one is at this point right here, and the coordinates again, we follow this down, and that's 7.5 clicks. It's always the X coordinate, then the Y, and 90 centimeters. We'll need those coordinates to calculate the slope in just a moment. Next up, it says what type of graph and written relationship between the variables is shown by this graph. And when we take a look at this, we've got a y-intercept that is 0, and we've got a positive constant slope. So we would say that this relationship between position and clock reading is directly proportional. Follow the steps to find the specific equation for the line. Looks like we still need to calculate the slope of this. So I think I'm gonna go ahead and do that over on here just because there's not a space for it on this other sheet. I'm gonna start by writing, I forgot my title, position. And you could use the symbols instead. You could either write position versus clock reading, or you could also do it with just the symbols. Position versus clock reading. Let's go ahead and calculate the slope in this empty space we have up here. We're gonna say the slope, just like a math class, is rise over run, or change in y divided by, that y doesn't look very good, change in x. The change in ry happens to be change in position, so we'll do change in position divided by our change in x would be change in clock reading. Normally we'd say y2 minus y1, but because we have positions, we'll say position 2 minus position 1 divided by clock reading 2 minus clock reading 1. And then we're going to go ahead and use those coordinates we have over here. This is our first point. Here's our second point because it happened 7.5 clicks. This one's at 10 clicks. So our second position is 120 centimeters minus 90 centimeters divided by 10 clicks minus 7.5 clicks. And we know that 120 minus 90 is 30 centimeters, and 10 minus 7.5 clicks would be 2.5 clicks. And 2.5 goes into 10 4 times. So that would go in here. I think that's going to turn out to be 12 times, but let's check it with a calculator. 30 divided by 2.5 equals 12. And we got an answer, or a slope, of 12 centimeters per click. And that's our slope. Next up, they've asked us to follow the steps to write a specific equation below, and I'm going to write y equals m times x plus b. We replace y and x with the name of our y and x axis, and our y-axis was position. So for our specific mathematical model, we'll write position. We'll fill in the value in units of slope in a second. The name of the x-axis was clock reading. The specific value in units of our slope was that 12 centimeters per click that we came up with here, plus the y-intercept. Where did the line cross the y-axis? And it looks like it's right at about 0. And we can plug in any clock reading here and find the corresponding position. So I'm gonna write final position because that's what we can use that to click out. It then says use this to determine the position of the clock, of the BB at a clock reading of 4.5 clicks. So where is the clock reading gonna go? It's not a position, it's a clock reading. So we'd say position final equals 12 centimeters per click times 4.5 clicks plus 0 centimeters. According to order of operations, do we multiply or add first? We multiply. And 12 times 4 is 48, and a half of 12 is an extra 6, so this would turn out to be 54 centimeters per click times click. Clicks cancel out, so this is just centimeters plus the original 0 centimeters And so our position at 4.5 clicks would equal 54 centimeters. So that's how we can use that equation to solve a line. Trying to make sure I can see that that is a vector up over here. Kind of box it out, and then use the graph to determine the position at 4.5 clicks. Compare your answers. Oh, we're supposed to look at our graph, 4.5 clicks. Here's 4.5 clicks. We go up to the graph, boom, and that looks like it's just before the 55 centimeter mark, and that looks like it's 54 point something clicks is what I got off of that. It's also important to realize that with this specific mathematical model that you should know how to write the general equation. Anything that's just straight up a symbol, you can leave it that way, like position final is equal to the slope of 12 centimeters per click is the average velocity of our BB times clock reading is already a symbol. And then the y-intercept, 0 centimeters, right? It's 0 centimeters tells us the position when the clock reading equals 0. So that would be the physical significance of the y-intercept. So this would be a general equation where this is a specific mathematical model. Where this is a general equation. Anyway, so again, for your graph, make sure you've got a title. You've labeled the y-axis with a name and units. Labeled the x-axis with the name and units, independent variable here, dependent variable here. Make sure you've shown the calculations on how to scale things. Put your values for scale on each of the graphs, plot your points with point protectors, draw a line of best fit, find 2 slope points and their coordinates. Please include the units in your calculation. Use rise over run or change in y over change in x to find the corresponding slope. Fill that in for your specific mathematical model, and you can use that to solve problems, and it can be reinforced by looking at the graph. I hope that helps.